Away. Yeah, thank you for inviting me back. It's a pleasure to be back on the Carnegie campus and to talk to you all a little bit about some of the work that I've been doing in my research group. As you remember from Peter's introduction, I'm diversified into a lot of these sort of different planetary scale investigations of looking at the surfaces of bodies through the surfaces and into the interiors. And this is a direct sort of extension of the work that I've been doing here on our favorite planet, Earth, which we all live on. It's very easy to access. And when I was over at NASA as a postdoc, one of the things that sort of I got interested in was, well, how can we take studies that we do here on Earth and use that to increase our knowledge about how we could actually study the other planets out in the solar system. And so one of the projects that I got involved in was thinking about these icy ocean worlds that sit in the outer solar system of our own solar system. And basically, what can we do here on Earth that actually can inform us the kinds of science that we might want to do on the surfaces of these bodies? So I'm going to talk a little bit about that research today. I'm obviously happy to take questions whenever people have them. I want to start by saying that this is not a project that's been done by just me. It's actually a whole cadre of folks who have been involved in doing this research across a whole variety of different institutions, including some of the logistics support for a lot of the field work that we do. So I'm not going to go through all the folks here on this slide, but I just want to point out that this is definitely not just my work. This is the work of a whole bunch of people on our team. And so what I want to talk about is basically the presence of liquid water. And this is something that is a key ingredient for life. And we know this on Earth because basically if you want to try and do abiogenesis, you probably need some sort of medium to do that. And so NASA's been very interested in where in the solar system you can find liquid water because of this sort of relationship to where biological activity could have gotten started. So I show a picture here of the early Earth. This is obviously an artist rendition, where you have basically oceans that have condensed out of this early atmosphere, creating little microenvironments where perhaps you can start to build the beginning of life on those planets and on our own planet. And so taking this out into the solar system, the question is, where is there liquid water today? So if you want to find an environment where life could potentially exist today, you're probably going to have to find someplace that has liquid water. We have one place that we know has liquid water and has an abundance of that. It's obviously Earth. We live on the water planet in the solar system. But we also have evidence for at least past water on the surface of Mars by looking at the geology and then examining these environments up close with all these rovers that we've deployed to the surface. Perhaps there's still liquid water somewhere down inside beneath the surface. We also have these big ice giants out in the outer part of the solar system, which somewhere in their atmosphere there is some sort of liquid water present. And then we have all these icy ocean worlds out in the outer solar system as well, these moons that orbit the gas giants that have shells of ice and then in some cases underlying oceans that basically sit beneath the surface. So there's a whole variety of different kinds of environments out there that might potentially host liquid water, which then makes them of interest to NASA for this exploration program, looking for environments where there could potentially be life. And so I'm going to focus today, in terms of my discussion, because we could go through a lot of these different bodies and talk about them, on Jupiter's moon Europa. Here's a nice picture of Europa orbiting around Jupiter. For those of you who might not know a lot about Europa, basically this sits about twice the distance from Earth's moon to Earth in terms of its orbit around Jupiter. It's about 5 AUs from the sun, so 4 AUs further out in the solar system, so you can imagine the conditions are much colder. And it's also tidally locked with Jupiter, similar to our own moon with Earth. The size of Europa, it's probably about just a bit smaller than Earth's moon, 90% the size of Earth's moon. It has a mass that's a little bit less than Earth's moon as well. And then we have a mean density that's on the order of 3 grams per centimeter cubed. Comparing that to the moon, it's a little bit less dense, and this is probably telling us something about the interior, meaning that there's a little bit more ice involved. And then it has a mean surface temperature that ranges between 50 to minus 125 Kelvin. So it's a very cold environment that we're dealing with. You can kind of pull away the surface, and basically we have an ice shell. It's maybe 2 to 30 kilometers thick, variable in thickness across that surface. Then we have something on the order of about 100 kilometer thick liquid water ocean that sits beneath that. And then getting more speculative as we move down into the interior, there's probably some sort of rocky mantle and crust, and then maybe a core of indeterminate composition. What's really interesting about Europa is that the surface of this moon is relatively young. It's on the order of 50 million years in age, so it's a relatively geologically recent surface, meaning that there's something going on that's modifying the surface and renewing that surface, all right? And so this is kind of an interesting, fascinating, geologically active world that can tell us maybe something about what's going on with where this liquid water is coming from. So if you were to compare the size of the European ocean to the size of the ocean, or at least the liquid water that sits on the surface of the Earth, it's actually about 3 times more water than we have in Earth's oceans. So this is truly an ocean-type world. I mean, Earth is an ocean world. Europa is definitely an ocean world in terms of the total volume of water that sits on this moon. If we kind of take a closer look at the surface of this moon, you see all kinds of evidence for this recent geological activity. We have these things called chaos, where basically you have what looks like the ice shell essentially being fractured and then refrozen. There's all these sort of fissure systems that cross-cut these big blocks of ice. And basically this jumble of materials, not dissimilar to what you would see sort of in the breakup of an ice shelf on Earth, maybe minus the fissures. There's these lobate kind of cuspate features that you see on the surface that are related perhaps to tidally driven fissuring and basically migration of cracks in the ice shell. And then we also see evidence for things that look like perhaps cryovolcanism. Basically, you have liquid water being erupted or all of volatiles being erupted onto the surface, basically similar to how you would have maybe silicate melts erupting in the form of a volcano, and they're leaving these big flow deposits that you see at the surface. So lots of evidence for this really interesting recent geological activity. And so you might be wondering, well, how does this place have the energy to drive all this activity on the surface? Well, the idea here is that Europa is basically a tidally heated world. You have the orbits of Io, Europa, Ganymede around the parent body Jupiter are basically interacting in such a way that you're dissipating some of that rotational energy into tidal energy that goes into the interiors and the shell of Europa and essentially generates heat. So that heat then can drive this geological system. All right, and if you were to sort of estimate what that heat flow might be, it's something on the order of 10 to 100 milliwatts per meter squared. We don't really know the exact answer because we haven't actually been there to measure it. But if you do the modeling, you can come up with this idea of how much energy might be deposited into these ice shells. And so that gives you these models for basically you have heat from the interior that's being transmitted into the ocean, probably through some sort of volcanism. And then also tidal flexure of that ice shell is also putting heat into that system and perhaps creating convection in that 30-kilometer thick ice shell. We also have evidence for very recent activity at Europa. There's a study that was done with the Hubble telescope looking at potential plumes from the southern polar regions of Europa that people inferred that maybe there's something like what's going on in this artist rendition of essentially material erupting into the space around Europa and then essentially bringing that maybe ocean material up to the surface. So if you were going to go to Europe and do a mission, you might want to see if you can either detect those plumes and fly through them like they did for Enceladus around Saturn, which is Enceladus is a moon of Saturn that has these eruptions at the southern polar region as well. And so there's all this sort of interesting evidence for basically recent activity, perhaps even activity as recent as today. So this has motivated basically an exploration program that would want to go back and interrogate some of this structure. We don't currently have any ways to image, except through telescopes, the surface of Europa. And we would want to go back and start to look at some of these in higher resolution. So this has motivated the NASA Clipper, which is actually under development right now for flying, and it would dip down and do flybys of Europa. You can't stay too close to the moon for very long because of Jupiter's radiation belts. And maybe try to sound through that ice shell and look at the plumes, if there's any plumes there, and get high-resolution images of the surface, which would be in preparation for maybe a follow-on mission where we would put a lander down onto the actual surface of the moon, and thinking about what kinds of signals that we could then look at from that, all right? And so my sort of take on this is that if you want to look through this ice shell, one of the best ways to do this is actually to use seismic waves. So you can actually sound the thickness of the ice shell, you can look at the properties of the underlying ocean, you can listen for, maybe melt migration through that ice shell. You can see the seismicity associated with that. We could see the tidal flexure. We can measure out the kind of seismicity that comes from this tidal cycle. We could actually see the tidal cycle itself with an instrument that we put down on the surface. So this is a lot of science that could come out of basically putting instrumentation down onto that surface. Obviously, we haven't been to Europa or even been to one of these icy ocean worlds. So to prepare for that, some of the kinds of things that we can do are modeling to predict the kind of ways waves would interact with this ice shell. And so here's a simulation I'm just going to show you where we've put in basically a layer of ice that's about 25 kilometers thick, a nice big ocean layer, and then some rock underlying this. So we just put the properties of those materials into our simulation. And then we can run seismic waves through that, basically using a forward modeling approach and make predictions for the kinds of waves and how they would interact with this ice shell. So a lot of sort of preparatory modeling that goes into trying to predict the kinds of waves that we might see at Europa. And then we can kind of start to think about how you would use those waves to sound that crustal structure. So if you have a seismometer sitting on the ice shell, and then you have some distant ice quake source array, meaning there's multiple ice quakes that are happening in the Europa ice shell, those are going to send out energy that then bounces around through the interior, interacts with the ice shell, and then with some seismic processing techniques, and I won't get into the details here, you can actually start to separate out, say, P&S waves, and then start to look for arrivals that are coming in from these different reverberations that are reflecting off the ice-ocean interface and maybe even the ocean-rock interface underneath, right? And this is basically using a single seismometer kind of approach. We can also start to get into estimating how much seismicity there might be on the surface of Europa and where it might be active. So this is from a recent study with Terry Herford over at Goddard, where basically we've used the tidal flexure model of Europa to predict where the energy is being dissipated within that ice shell, and then associating that with essentially a generation of seismicity. So I'm going to run a little model here so you can see it. Hopefully this will work. Okay, and so what you're looking at here is the evolution as you go through that orbital fraction around Jupiter. The dissipation is shown here in color. So the red is basically where you're dissipating a lot of energy, and then the blue is where you're dissipating less energy, and then the black dots are essentially seismicity that's being induced by the stresses that are being put into that. And so you get basically this pattern of where you might predict seismicity to take place, and then we can map out sort of the peak accelerations that are taking place from those various events, and these are scaled to sort of the moment release that's taking place. And then estimate, okay, where are going to be the best places to put a seismometer down so that you can actually record these ground motions. All right, so in this diagram here, the darker areas are sort of the places where you're going to get the peak accelerations, and the lighter areas are where it's going to be potentially quieter. So it sort of depends on what you're looking for. If you're trying to see all the nearby seismicity, you might want to go to a nice quiet spot so you can see the big events. But if you want to catch all of that little local seismicity and look at all that ice quake cracking, you might want to go to the places where there's going to be a lot of activity from those nearby events. I'm not sure if this next part's going to work, but basically we have a simulation of the waveforms of those, and then we can speed it up and play a sound clip of that, and it doesn't look like this is going to show up on me. Oh, I'm sorry about that. One movie here. It's all right. Basically what we do is we just speed it up, and it makes this sort of eerie mood music that you can listen to of earthquakes bouncing around inside of Europa. If people are interested, I'll pull it out later, and we can play with it. Sure. I think it has to do with first of all, you're seeing the projection here is kind of exaggerating the size of the poles, but it has to do with that sort of shape flexure. I'm not sure exactly why it's being concentrated at the poles, but this is sort of the model that Terry was using. Yeah, I mean, I'll have to get back to you on that. I don't know the answer off the top of my head. Okay. All right. So thinking about, okay, what could we do with preparing for that sort of next step of what we can do on a lander? One of the things we want to start to figure out is like how many events can we actually expect to see in a 20 to 30 day mission? And you're probably thinking, why only 20 to 30 days? Why don't you just go there for years? Well, that's sort of the expected lifetime of a lander on the surface of Europa. There's a lot of radiation in that environment, and so your mission duration is very much truncated by the fact that you're only going to be able to see maybe about 10 orbital cycles around Jupiter before your instruments are fried by all the radiation. We also need to figure out, do we need to send like the Cadillac of seismometers, the most sensitive instrument, or can we get away with sending something that's a little bit less sensitive because of the sort of background seismicity and noise that we would expect at Europa? And then we also want to think about, from sort of like the kinds of models that I was showing here just a minute ago, where would we want to put that instrumentation on the surface? All right, so figure out what's sort of the optimal location that you can actually deploy that instrument onto the surface. And then thinking about what kinds of signals would we want to record with that instrument. So do we need to make it more sensitive in a particular frequency band or another to try and determine, okay, the best way for us to actually detect these events. And then, of course, there's sort of the sort of nuts and bolts of thinking about how do we get that seismic data back to Earth. Because if we collected a really high sample rate, maybe there's too much volume of data for us to actually transmit back. And so how do we do either onboard processing or some sort of compression algorithm to push things back so we can use basically the sort of thought experiments to figure out, okay, how much engineering do we need to put into this to get this information back to Earth? And so this all sort of swings back to the idea of using Earth as a place that we can actually study this, because we can actually do these kinds of experiments either on the computer, or we can go to analog environments here on Earth and actually make these kinds of studies to actually constrain what we would need to do with the mission. And so if you're going to do an analog for Europa on Earth, there's a couple of ingredients that go into that. You're never going to have 100%, 100% resolution or fidelity to what might be happening at Europa. But we can find places that are somewhere in between, and then we can use our understanding of the scaling to move the physics back and forth between the different bodies. And so one of the environments that we're looking for is basically a thick ice overlying some sort of liquid water, perhaps rock underneath that, to capture some of the physics of that wave propagation that you would expect. We're also looking for sources of seismicity that are taking place within ice, so that we can actually look at the sort of, seismicity in ice is a little bit different than seismicity in rock, so that we can actually study those physics and make sure that our scaling is taking into account some of the differences in the way the ice quakes are generated in that material. Ideally, we'd like to be able to decouple from any atmospheric effects, which of course is impossible on Earth because we live in this nice thick atmosphere that makes our lives pretty easy. But it makes a lot of noise that will contaminate whatever signals you're trying to see on Europa, which is an airless body. And then to think about the actual equipment that might go to the surface and how that lander will act as sort of a filter between you and what's coming from the interior of the body. And so if you put your instrument up on top of the lander versus on a leg, or deployed it directly onto the surface, how that's going to actually affect your ability to record that information. This was a big problem with the Viking lander, where they had the seismometer put up on top of the spacecraft. And so when it landed on the surface, all it recorded was basically the Viking spacecraft vibrating in the wind. And so InSight rectified that problem 40 years later by going there and putting the instrument directly on the ground. So, are we going to have the same kind of problem on Europa? Probably not, but just sort of figuring out what the lander is going to do to you, I think, is an important step that you want to examine before you actually get into that. Okay, so I'm going to change gears a little bit here and talk about some of the work that we've been doing here on Earth, as basically using our planet and the cryosphere parts of our planet as these analogs for Europa. So here's a nice simulation of what the Greenland ice cap looks like here. And so we're going to be basically traveling there and thinking about some of the science that we can use to prepare for this kind of outer solar system exploration. And so for those of you who don't know about Greenland, it's been in the news recently for some very odd reasons, but it's basically an autonomous country within the Kingdom of Denmark, all right? So they have their own government. The native people are the Inuit, and they've been there since about the 13th century. And it's also the largest island on Earth. I don't have any Australians in here who are going to take issue with that, right? But it has a human population of about 56,000. So this is actually, the whole population of Greenland is smaller than the town I grew up in, Iowa. The geology there, it's the second largest ice sheet on Earth, which I'm pretty sure anybody here can guess what the other ice sheet on Earth is. The ice cap itself is about 18 million years old, so it's been around for a while. And then some of the oldest rocks on Earth are found in Greenland, so it's definitely got some really interesting geology that people are interested in. And then there's an average temperature of about minus 20 degrees C, so this is clearly an icy environment, and this is at the center of the ice sheet. Okay? Despite the fact that it might have this sort of cold environment, if you've ever flown over Greenland in the past couple of decades, and happen to look down during the day on a non-cloudy day, you'll see all these aquamarine lakes that are basically cropping up. This is one of the margins of the ice sheet. And this is because Greenland's been basically melting fairly rapidly, on the order to the tune of about maybe 200 cubic kilometers per year. For reference, that's about 200 Mount St. Helens eruptions per year in terms of the volume of material that's coming off of the ice sheet. And we've seen evidence of this in terms of an acceleration of that melting. There's the formation, obviously, of these superglacial lakes. We've also seen subglacial lakes where you have water basically getting down to the base of the ice sheet and then essentially pooling. There's a couple of studies that just came out here in recent years that have identified up to 50 or 60 actual subglacial lakes that have appeared in the last 10 years or so. And then we've also seen water basically trickling down into the FIRN at the top. It's sort of the equivalent of a gravel and sand aquifer on Earth, or silicate bodies. Basically, you're storing water or transporting water through the top of the ice sheet. So we have all this melt that's going into that system and then ultimately ending up in the oceans. And so global sea level rise right now is about 3.3, 3.5, depends on who you talk to, millimeters per year, and about a quarter of that is being attributed to all this melting that's taking place in Greenland. Okay, so we have this sort of event of melting a continental scale glacial landmass and basically translating that into the ocean. The last time something like this happened was the end of the Pleistocene, when all the North American and Asiatic ice sheets melted and basically disappeared into the oceans. If people are interested, this would translate, if you took all of Greenland and melted, it's about 7 meters of sea level rise. So go check your elevation and where your cabin is out on the bay. We can take I have some pictures of some of this melting. So this is one of the fjords here where we have a glacier calving off into the water here. And a lot of these have retreated tens of kilometers to hundreds of kilometers, depending upon where you look, based upon that sort of melting. This is one of the primary mass loss mechanisms, essentially glaciers flowing into the ocean. This is a picture of sort of a deglaciated fjord here, which is obviously very scenic. Geologically young places tend to be really pretty. And we can see all kinds of evidence where you've exposed that sort of subsurface bedrock. The Danish Geological Survey is out there in Greenland every year, mapping new deposits and looking at new rocks. There's all kinds of stuff that's being uncovered as the ice sheet retreats. Perversely, this is a lot of oil and gas deposits that could help accelerate the whole retreat. We see ice flooded with water. This is the top of a glacier. So you actually have ponding of these lakes and forming at the surface. And then, of course, these are massive icebergs and the sort of earlier breakup of the sea ice itself. So there's all these things that are going on in Greenland right now that tell us something is afoot. So the work that I'm going to show you here in the rest of the talk is actually from 2 different field sites that are on opposite sides of the island. The first one I'm going to go through is the study of a FIRN aquifer down in Helheim Glacier in the southeastern corner here of the island. And this was an NSF-funded grant with the University of Utah, where we did a bunch of active source seismic surveying and other kinds of techniques to try and look at this FIRN aquifer. And then the second field site, which is way up here in the middle of nowhere, and up near Thule Air Force Base, which has an interesting history that if you have, if you want to talk to me about that over lunch or something, I can tell you some interesting stories. This is where all the B-52 bombers flew out of during the Cold War sort of nuclear scare back in the 50s and early 60s. This is a NASA-funded grant where we're basically looking at a subglacial lake that was detected with radar overflights up underneath the ice sheet there. And we were basically running an experiment to test what would a Europa-style lander mission actually record if we were deployed onto that over that lake. So let me start with the first field site. So this is our FIRN aquifer site down here in southeastern Greenland. The idea here is that you have snow and FIRN, the surface. FIRN is basically like recrystallized granular snow. It looks kind of like sand if you look on a hand lens, on the order of a few millimeters in grain size. It has a lot of porosity, so if you take liquid water and it can percolate down through this, and because of the latent heat of fusion, basically you can have this two-phase system where you have solid ice and water coexisting on equilibrium for all matters of purpose. And that can store that water and it'll flow downhill just like you would in an aquifer on a slope here, and eventually it finds its way into that glacial system and perhaps drains out into the oceans, or it gets stored in the aquifer. We're still trying to determine the answer to that. So the field site kind of transitions from the accumulation zone where you have this basically a snow field to where you get into places where you're starting to deform the ice and it's speeding up because you've wetted the bed, and you get these big fractures and cracks in the surface called crevasses. And then, of course, then the glacial front here where you're calving all that material off into the ocean, then you have the ocean itself. So one of the questions I often get for people is like, well, okay, you went to Greenland, well, how do you get there? So I'll talk a little tiny bit about the actual traverse to Greenland. So my first field site, we started here in Washington, D.C., took a very cushy Air Iceland flight over to Reykjavik, and then flew back to KULUSUK in Greenland, so all by commercial air. So if you ever want to go visit these locations, you can do it with a relatively cheap ticket, because Reykjavik, they're always trying to encourage people to come there for tourism. And then the local flights back to KULUSUK are like once every day or so. So you can actually take a flight to Greenland directly. And then to get up to the ice sheet, we just had helicopters that would move us and all of our gear up there. Here's a picture I showed a little bit earlier of KULUSUK. This is in I think this is in late July, so we still have icebergs and stuff coming out from the fjord. There used to be a glacier here probably about 50 years ago, but it's since receded back about 50 kilometers over the last 50 years or so. You do the math on that. This is the luxurious two-star hotel KULUSUK, which is the only hotel in town, and it basically serves all the people who come through, a lot of tourists. And then here's KULUSUK itself sitting sort of on the fjord with all the sort of Norwegian style coloring of the houses there. It's about 300 people who live there. The primary industry is hunting and basically fishing. So there's a lot of people with boats. You don't have a car on KULUSUK, you have a boat. To get around onto the ice sheet, this is the team of folks. We are out there for 2 different years. We basically have a helicopter bring all our gear in, sling loading all of your thousands and tens of thousands of dollars of equipment underneath of a helicopter that the pilot can drop into the ocean if something goes wrong, so that's a little nerve-wracking. This is actually me getting ready to hook it up to the helicopter, that's kind of an exciting experience to have this ton of stuff basically going freewheeling while you're standing next to it, so you gotta watch what you're doing. But yeah, so this gets all of our material up there. We're staying in these Arctic oven tents. Basically, this is one of the sleeping tents. You can see the sort of arrangement here to sort of avoid the wind, our gear lines. And the surface would freeze in the evenings. The sun would sort of just dip below the surface. We were far enough south there that we actually got a little tiny bit of night. And in the morning, you'd wake up to this sort of glare ice, frozen surface, and by the afternoon, it'd get kind of mushy and melty. Okay. So that's basically where we're working to try and investigate this FIRN aquifer system that was detected in these radar overflights in previous years, where people are basically flying these Operation Icebridge airborne radar over the surface of Greenland, and in places they'll see this radar reflection from these aquifers in the subsurface. So let me sort of go through that a little tiny bit. This is a zoom in on our field site near Helheim Glacier. So here you can see the glacier coming down this valley here and then hitting the ocean and the fjord. And then these lines here are showing you where basically all the overflights were through this area. And then the colors here indicate the detections of basically a water table just below the surface on the order of 5 to 20 meters or so beneath the subsurface. And so our field site basically is we deployed into this region here to actually start to look at these in more detail and get a much closer picture of what's actually going on within these aquifers. And so this is a typical radar overflight of this region. So I'm going to show you, here's an elevation profile, all right? And then this back here, I think, is the slope of that surface, all right? So where there's big changes in slope, all right? And then underneath of this, I'm plotting the radar itself, so you can see the reflectivity of the subsurface. And so you see this really bright reflector coming in sort of at this sort of bouncy, jaggedy surface here, which is actually parallel to the topography at the surface. So if you were to correct for the topography on this, you'd see this water table that sort of follows the slope downhill, all right? So this is from actually a ground-based radar. This is from the overflight radar. So you can see that there's fairly good correlation between the location of that water table between the 2 different radar types, the one that's ground-based versus the one that's aerial-based. But this has much higher resolution because we're using a higher frequency radar to do that, all right? And so basically, we can see this aquifer, we can see the top of it, but the problem is that we're not actually seeing through it. We don't know how thick it is, what's the depth extent of it, right? So people have gone out and they've sampled this with cores to basically see, okay, how far does that aquifer extend? But that only gives you a point measurement, right? You're not able to see overall this whole section here, how that aquifer base is changing. So this is one of the things that we wanted to go out there and do, is actually measure and use some geophysical techniques to get at that. And so here's our field site. Here's the Helm Glacier. We're about 30 kilometers or 20 or 30 kilometers up from the terminus here. And then we have this line here where we studied basically the properties of that aquifer through that area. Here's a satellite photograph of our camp, so you can see the housing. Here's one of our gear lines. I'll let you guess what that thing is that's downwind. And we did a whole suite of different types of measurements out there. So we cored the ice to take measurements of the noble gases and look at the atmospheric evolution and date the age of the ice. We did some magnetic resonance, ice penetrating radar, seismology, and then a whole sort of kitchen sink worth of hydrological experiments to measure the properties of that aquifer. And then we also installed a weather station that basically could monitor the conditions of that site between year to year. So here's just a diagram or pictures of some of the things that we were doing out there, right? Digging snow pits, coring down through the ice. This is me doing a seismic active source shot with a makeshift source using a snow shovel. We did have a hammer, but it somehow got removed from the first flight out, so we had to wait for the next flight of gear delivery. And then putting in a whole bunch of equipment to actually measure the actual properties of the aquifer, taking some ice cores. Here's me holding one where we've actually sampled into the glacial ice beneath the aquifer itself. We also did pump tests where you're pulling water out of the aquifer so you can get the best cool drink you've ever had. I have a marketing scheme if anybody's interested in investing in Greenland aquifer water. And then of course the hydrology. I have to tell this story because this is a fun story. So this person here, this is Lynn Montgomery, who is a undergraduate who kind of won the lottery and got to come out into the field with us. She turned 18 on the ice, and it was her first field experience, and she had a great time. She got to do tasks like helping Olivia here, who's a graduate student at the University of Utah, try to capture some water in these copper tubes so that they could do these noble gas analyses. And basically what you do is you pump water from the aquifer into these pipes, and there's water spilling everywhere, right? So that's why they're wearing a tarp. So 0 degree seawater spattering everywhere. You're getting wet in the tent. They're having a fun time, I think. It was a good field experience. Lynn would do it again. That's what she tells me. Okay, so let me talk a little bit about the seismic science that we did there. So we were doing active source interrogation of the subsurface. So the idea here is we're refracting waves through the layers in the subsurface and seeing how those waves churn through that medium to measure the seismic velocity and figure out what the velocity profile is with depth. Basically, you take a hammer, hit the ground, it creates waves that propagate out, and then you can pick on the P wave arrival and make a measurement of the actual velocity. I love this diagram because it shows the proper organization of a field experiment. You have a professor overseeing the postdoc who's doing all the hard work, right? That makes sense, right? Undergrad is learning how to do everything and monitoring it, right? So the seismometers themselves are actually set up in a little line that we just kind of stick into the snow, and you can see it going off here towards this weather station in the background. I really love this data set. If anybody ever wants to work with it, please get a hold of me. It almost looks like synthetics, just how clean it is. I'm used to looking at terrestrial data. Yeah? So we're on FIRN, so you need to have something to hit. So in this case, we put out a metal plate, maybe like a little piece of airplane aluminum that's about half a centimeter thick, or a centimeter thick, and basically just hit that. And if you do a lot of hits on the same spot, it starts to sink into the surface, but it compacts pretty quick. Okay, so this is just showing you a little bit more of that data. This is from a shot gather here where you can see this beautiful P wave coming in. We see some surface wave dispersion here. There's the air wave, which is the sound of the hammer hitting the metal plate traveling through the air. And then we also get, and this is gained up a little bit so you can see it, but the reflection from the ice rock interface about 1 kilometer beneath us. So this is with a hammer and metal plate. I can see 1 kilometer into the ice sheet basically and see that interface beneath, but we can also see these waves that are churning through that. And so then we use a Bayesian technique to actually model this. So here's the travel time picks that we get from, say, one of these profiles. And then we can go through and try and fit basically the velocity curve that would explain those travel time delays and try a whole bunch of different models that fit the data with some uncertainty and basically come up with an error bar for what the variation is at depth. So the results of that, it looks something like this. So this diagram here on the left is where the Bayesian approach is basically finding discontinuities or jumps in the velocity structure. And so you can see there's a nice big jump around 20 meters depth that's basically associated with that transition of the materials into ice. And then we can also use that sort of ensemble of models to calculate the uncertainty or the likelihood of the velocity model as a function of depth. So you can see that this transition is very strongly constrained by the data. The velocity structure in the upper part is more of probably a gradient than a layer structure, which is why you get this sort of distribution here. And from that, we can construct basically a 1D model of that particular refraction line. And of course, you can extend this to 2D and do more sophisticated structure, but in this case, we're just trying to see where that transition to ice is taking place at the base. So we did this whole suite of measurements. So here's showing you for a site where we had a core, a seismic profile, and then also a measurement of the density of each of the cores by taking basically the core itself and then measuring its volume and mass to figure out what the density structure is. So we can get a lithology, the stratigraphy of the core. We can measure where the water table is detected by the GPR. We can also see where that transition takes place to pure ice, where you essentially lose the aquifer. And make a comparison for the sort of ground truth sites that we have to use to calibrate sort of our eye what we're looking for in that structure. And you see the transition into ice sort of associated with the seismic profiles. We don't necessarily identify the water table in the seismic, and that's something that's a little bit more involved in a sort of a difficult discussion to have in just a couple of slides because of the way the resolution of the waves work. But also we see this sort of correlation with where the velocities go up with where we call clear ice, which we think is essentially frozen aquifer, places where the aquifer has actually transitioned from liquid water into proper ice, and it essentially fills the pore space and gives you this beautiful clear, glass clear core, which you see ice all throughout this, but it's generally kind of have some air bubbles frozen into it. With the aquifer layers, you see that you remove that air. So we can take this measurement and do it at a whole bunch of different sites, which we did active source at all these different sites along this profile, and essentially get an error or an estimate for the amount of porosity that's present within the aquifer, and also figure out the thickness of that layer, and then estimate the abundance of water that's present. So we know from the radar where the water table is. From the seismic, we can get the base of the aquifer, compute a thickness, then we can look at the velocity difference between the underlying ice and the aquifer itself, and actually compute a water content from the porosity. And so as we go down slope, basically you see there's this gradual increase in our computed water content from the seismic profiling. And this corresponds basically with what you kind of expect. As you go down slope, you're filling more of that pore space. There's more liquid water entering into the system. And then there's some 3D effects from out of plane where you maybe are going over sort of a dry spot where the water's flowing around that location. And what we see is essentially there's a 1 or 2 kilometer upward expansion of the aquifer between 2015 and 2016. So areas that were dry before are now getting water stored in them. And if we extrapolate our water content to from what we see at Helheim, which is about 4.5 gigatons of liquid water, to all of Greenland, that gives you about 140 gigatons of water in all the aquifers that have been detected around the Greenland ice sheet. And that works out to about 0.4 millimeters of sea level rise. So if you remember back to the overall budget of Greenland water is like 25% of 3.3. So the aquifers have the potential to be a significant fraction of that overall contribution. The problem is we don't know if that water is being communicated into the inglacial system and then making its way out into the ocean. So it could be that the aquifers themselves are actually potentially storing a lot of water that could then subsequently be released and add almost another 50% to that total flux of water that's coming out of the Greenland ice sheet. And so that's sort of a TBD on this particular problem. And so this kind of leads to this model that we've come up with of essentially the base of the aquifer is this, this frozen layer that's sort of where you pass the thermal gradient and such that the water essentially freezes out and gives you ice. And so that sort of creates a thermally controlled base. And then this aquifer is sort of filling up as you go down slope, and essentially you're transporting more material. And eventually either that gets frozen in down by the crevasses or then drains into the crevasse system, and then it ultimately maybe finds its way down to the bed. And if it can get to the bed, then it can find its way into the ocean. Okay, so that's the first field site that we were looking at. What's really cool about this field site is it got me thinking about, okay, what can we do in these kinds of environments? What kind of science can we do to apply it to these other bodies? And we've had these measurements of basically the properties of ice. Note that it's relatively warm ice, right? So you can think about the attenuation and that kind of thing, and we can use that kind of information to inform how we might extrapolate back to Europa. The next experiment that we did, which is this field site up in northwestern Greenland, we're looking at basically a perfect analog site. We have this subglacial lake with about a kilometer of ice above it. And that subglacial lake probably formed recently from either a transport of recent meltwater to the surface, or perhaps it's more ancient and it has some sort of saline component to it that's kept it liquid. The local topography in the bed, which is shown here, is basically what's driving the formation of the lake. You have a little bowl that basically can gather that water. And basically, the water itself hasn't really been detected until we have these sort of high detailed radar overflights that show essentially this radar flat surface beneath the ice, which is interpreted to look something like this. This is a lake we spotted when we were coming off of the same region that's been deglaciated, and it's sitting basically here on the local topography where the bed, where you imagine a glacier being sort of over this, there would be a little lake here. The field site itself is basically this flat white plain. It's like being on the surface of the moon minus craters in a blue atmosphere. Getting to this particular field site's a little bit more involved. We had to take an Air National Guard flight up to Goose Bay, Canada, up to KULUSUK, where we geared up, and then flew up to Thule Air Force Base, and then took a helicopter flight up onto the ice sheet. And then so you spend a lot of time in transit here to actually get there. Here's what one of those flights looks like. You basically get to sit in the back of one of these C-130 cargo jets, and all your gear is palletized and basically sitting with you. Here's some of our sleds. You can see all of our boxes with our equipment. We picked up all of our survival gear in KULUSUK at the, we call it the International Science Support Facility, which is basically where all the polar scientists who are working in Greenland go through there to get their gear. We have a concern for polar bears in this particular location that we were working at, so we had to go through polar bear hazard mitigation. And part of that is making sure that you have knowledge about how to use a weapon to protect yourself in case a bear tries to eat you. We worked out of Thule Air Force Base, which looks a little bit like McMurdo down in Antarctica from what I've seen. Basically a bunch of hangars and facilities that the Air Force uses for both training and monitoring operations. U.S. Air Force, actually Space Force now. The Space Command is centered up there, which will be interesting. Basically, you spend a lot of time in the warehouses organizing gear, testing out your equipment, doing huddle tests, and then eventually you get to take a helicopter flight through Canuck Airport up onto the actual ice sheet. So here's our helo that did all of our sling loading, the team of folks that went up there, and then the camp that we actually occupied. I'm going to show a quick video here. I don't know if this will have sound or not, of basically a helicopter landing some of our gear onto the ice sheet. So yeah, it doesn't look like it have sound, but that's okay. It's pretty just loud. All you hear is a helicopter beating against it. But basically, here's our snowmobile and maybe a little bit of equipment getting slung load onto the ice. And he's going to drop it down here in our camp with all us waiting in eager anticipation. And then here's Sue's, our mountaineer, guiding the helicopter pilot, sort of. And you get to live in this little blizzard while they land. But it's pretty exciting to watch this stuff happen. It's one of the joys of the field work is getting to see these pilots work, because these guys are real flyboys. They know what they're doing when it comes to the conditions that they're doing up on the ice sheet. And they do it all in a really safe, efficient manner, which just blows my mind how they can fly in some of the conditions that we're working in. Okay, so he's going to go plop it down there on the snow. So you can kind of see here, here's our bear fence, that tripwire that lets us know if a bear happened to wander into our camp while we're sleeping. There we go, putting it down. So that's how you get up there. One of my favorite scenes, we're far enough north that you have 24 hours of sunlight. And so we put out some bamboo poles to give us an idea of orientation of north. So this is exactly midnight. You can see basically the shadow is pointing basically due south in this situation here. So the sun just kind of goes around your head. It's very dangerous because you can work all hours and not realize it's midnight. A couple of birds came out and joined us. I don't remember what these were. I think there's some sort of Arctic tern. And then a few days where we had basically just to dig our tents out in snowstorms. So, you know, variable conditions. Similar to our southeast experiment, we had tents that we work in. You know, here's your food tent, all your food in one place. So it's an interesting place to work. So let me get into the details a little bit of some of the stuff that we did up there. What we're interested in doing is basically mapping out the properties of this subglacial lake. So here showing you the inferred extent of the lake. We called our camp Camp Europa, very kind of fun. Here are these sort of lakes that I was pointing out earlier, sort of the same scale here that have been deglaciated. And we've had a field season in 2018 where we went out and deployed equipment, then we returned in August to remove that equipment. And we basically put out a whole bunch of seismometers. We did some ice penetrating radar, a little bit of active source seismology, and then we left a weather station and a GPS and to sort of monitor the conditions at the site. So here's a little bit of an overview of some of that science. Here's our little seismometer array. We had a lander that we buried underneath the surface here. That's basically our mock-up for Europa lander. Obviously, it'll be more complicated than this when it goes to Europa, but the idea is like looking at how the seismometer performs on different places on the lander itself, putting in a short aperture array to actually locate some of the seismicity so we can do ground truthing for where these things are located, and then a whole bunch of other measurements that we're sort of taking in that area. So here's the lander array. So we built this box around it to do this isolation from the atmosphere. So we basically dug down a hole. Well, me and one other guy dug a hole 2 meters deep roughly and about 3 meters by 3 meters there in size, buried this box underneath, put our lander inside of it. We had to dig the hole out a bunch of times because the snow would drift into it. But we had a seismometer put underneath of the lander here, a couple of different types of instruments so that we can monitor the effects of different instrument performance. We put some instruments at the edges of the box so that we can monitor any noise that was coming off of the encasement here. And we had something that looked kind of crazy with all these little Mevo boxes with solar panels coming off of it. And sort of the final product was basically all buried underneath snow. And so here's what it looked like. You basically have a bunch of panels that are collecting energy and then powering all the equipment that's underneath. We did some active source so we could actually monitor the performance of the array and look at some of the details of how it's doing recording, and then do this reflection profile. There was a whole bunch of ice penetrating radar that we did, but we also did an active source reflection line. This is Erin. She's going to demonstrate to you how to do a proper hammer swing. There you go. Note that feet didn't move. Controlled the cable, kept the hammer from bouncing, good job. So basically we did this survey out to sort of simulate what you would basically be able to do with a series of sources that would sound the ice, and then determine that sort of properties of the lake beneath us. And so I'll kind of cut to the chase here. Here's this line starting at camp, going up slope basically towards where you start to see this little subsurface topography. So this is like a mountain cliff or mountain slope here. And then the lake itself, this is IPR, ice penetrating radar. So all you see is the reflection from the lake and then from the rock ice interface. And then from the seismic line, we actually see that same interface. There's the lake, and then sort of going up that slope. But we also have all these reverberations, which are waves that are reflecting within that lake layer, basically seeing the depth of the lake, seeing the rock interface beneath it. And then this right here is actually the second reflection from the waves that travel back up and back down again. So if I had recorded for another second here, I would have basically seen the third reflection probably. So this is with just a hammer and metal plate, you're able to see through about 1 kilometer of really warm ice, which bodes really well for our ability to sound into the Europa ice shell. So on Europa, you could in theory do it with like a drill or some sort of standard explosive. Basically, they use these little tiny explosives to pop out solar panels and stuff like that. The NASA or Apollo astronauts basically had, it's like a cane with a bit of explosive on the base. They could just pull a trigger and it would do a shot. So you could do the same kind of thing with a robotic arm or just deploy a little charge onto the surface and basically create these waves that would reflect. So my postdoc, Ross McGuire, has been working on this with an undergraduate where essentially we've been trying to do the measurement of the lake thickness. So you'll get the, whoops, didn't mean to go forward on that. And so you can see the lake top and then the lake bottom and essentially quantify the thickness of that lake shell. So that's really cool. You're able to actually get through this and see what some of the properties of these lakes are. We've also been doing a little bit of science, I'm almost done here, with sort of the coherence between the lander and the ground to try and understand essentially how that lander would respond to the various seismic signals that are out there. So if we look at an earthquake, we'd recorded one of these ridge events, maybe about a 4.5 at our site, and you can see that the coherence between the instruments on the ground and versus the instruments that are on the deck is very high when you have a lot of energy coming into the system. And if you're just monitoring the noise, actually the lander has a very different response than the actual ground. So it sort of depends on what frequency and what kind of energy you're looking at and your ability to resolve things. So this is really good for our argument that you can put an instrument on the lander, because you should be able to see at least the seismicity. You might not necessarily capture the noise of Europa. So something to keep in mind. Okay, and so then we can get more sophisticated and basically make some models. So this is showing our lander with instruments on it, and then showing how it responds to some incoming ground waves, obviously very exaggerated, and it does a little lander boogie, which is basically related to sort of these high frequency resonances that we pick up. So we can actually start to get very quantitative about the kinds of signals that we would expect to see through our lander, and how that would translate to the motion we see on Europa. So this brings me close to the end. Basically, our goal was really to start to determine some of the properties of this material. And so we've been working on that right now. It's sort of work in progress, and we're trying to push this out into form of a couple of papers to try to understand the properties of that water underneath using our geophysical tools. And also, we've been going through and trying to find all the different seismicity that we recorded and automate basically ways to do that detection, so that you can kind of think of like, maybe we need to clip out little time windows of when there's some sort of interesting signal and send that back to Earth rather than sending back all the data. And we now have a test data set that we can work with that does that. We also have some constraints on the local ice dynamics and velocity using this GPS weather station, which is interesting from a sort of global warming sort of change in the actual conditions of the ice sheet, since you have this lake underneath, and we have some ground truth now of the ice velocities, which are predominantly gotten from INSAR and radar measurements. And basically, we're taking this sort of constantly changing melting environment and turning it into science that we can use to do this exploration of the outer solar system. So this is kind of my philosophical moment where I'm saying that, you know, global warming is certainly not great for us or our civilization. There's a lot of people that are going to suffer from it, but at least there's some opportunities for us to take advantage of these new environments that haven't been observed since the Pleistocene to do some really great science. So with that, I'll leave you with a little movie here of basically our weather station had a camera that was taking an image, I think it was once every hour, and this is just a movie of the site over the summer, so you can see how things change. So let me play that. And you can just watch the sun rotate around us as we take questions. All right? So thank you very much. Yeah. So most of the energy from the radar gets reflected off of that water table. It doesn't actually penetrate into the water itself. Now that said, if you were to take a really powerful GPR, you could probably see it, but even Operation Icebridge, which is flying state-of-the-art, still wasn't penetrating into that water table. So going out there and doing the seismic profiling was what we needed to do to get through that. Yeah, this is a problem with GPR and water. It doesn't like water. Yep. Connell? Yeah, that's a good question. And the regolith on Europa is going to be an interesting problem, because the sort of regoliths on silicate bodies tend to have a little bit more extensive depth, because the heat of fusion, the actual like resetting of that sort of grain boundary is relatively difficult to do on like the moon or Mercury or something like that. But in an icy environment, you're going to get basically ice welding and that kind of thing. So what would be an effective regolith, which a regolith, for people who don't know, is basically this fractured, broken up material at the surface that's created by all these impacts hitting the surface. And it's very disaggregated and doesn't have a lot of consolidation to it, which means it has a very low seismic velocity and also tends to scatter waves very readily. If that layer is relatively thin because of the sort of ice re-annealing onto itself, it's not going to have as strong of effect as, say, it does on the moon, or even maybe on Mars, where there's still silicates. Yeah, and I mean, you don't have to go very far within the Europa interior to actually warm things up, too, to the point where you can actually start to remove that regolith layer. Plus, you have all this geological activity that's overturning the surface, so a lot of the surface features are actually, you know, that regolith would get removed. There's not enough impacts onto the surface of Europa to generate the kind of regolith that we have on the moon. It's something a little bit of both, but I think if we look at the surface, we see these rifts that seem to be tidally opened and closed, and so you're adding material there, so you're injecting, basically like a mid-ocean rift, you're recycling material and churning out new crust, if you will. And at some point there has to be some sort of return of material, so people have postulated there's some form of subsumption or subduction kind of process on Europa that's removing that material from the surface and putting it back into the interior. But there's pretty good evidence that that ice shell is convecting, so you have that sort of mechanism for driving that resurfacing. Yeah. Plus there's volcanism that would put new materials on and layer things. Yeah. Yes, ice subduction. Okay. Yeah, we had a little snowstorm that covered it over, and you'll notice that it buries things. Yeah, about 2 weeks into our experiment, we had a snowstorm that dumped about 2 meters of snow on our site. We were expecting 2 meters of ablation. So we lost a lot of equipment because of that storm. And that's this storm right here, basically. But we still got data, so that's great. Yeah. Oh, the magnetic resonance sounding. Sure. Yeah, we didn't do MRS, this magnetic resonance sounding up at the Camp Europa location, but we did do it down in the aquifer there, and it's basically you go out and put a loop and basically run current through that, create a magnetic field that then you can change on the different frequencies and get an idea for essentially the liquid water abundance at depth. You're resonating those hydrogen atoms. The problem with it is non-unique. So you can do an inversion, but you need to have additional constraints to actually get where the water is sitting within that column. So yeah, in theory, you could do something like this from orbit, and people do talk about using EM sounding kinds of things. But if you're on the surface, yeah, you could certainly do magnetotelluric, and there should be some signals there. I don't know the details for Europa, what that would look like, but I'm sure that that's something that we could take advantage of, given we have this, we're in this interesting environment around Jupiter. You can use the sort of telluric currents that get induced by that in the ice shell, especially if there's liquid water present. But I don't know the details of how one would go about doing that, but people have been thinking about that for sure.